Hello everyone, welcome to my channel, and we have 4 circuits here. What is this? This is an LED flasher. We have 4 circuit, circuit. This is a commercially available circuit in the market. An RGB multicolor fast LED flasher. You can just buy this in the market at ease. RGB, red, green, blue color. Just connect a resistor in series. There you have the LED flasher. RGB, you can connect this in 5 volts, 9 volts, 12 volts. Another one, we have this, a blue blinker, LED blinker, also available commercially in the market. You just buy this blue blinker and connect another LED in series with the resistor at the back. This blue blinker is make this normal LED to blink. If you connect the LED blue blinker in series with this normal LED blue. Now we also have this. You know what is this? This is a circuit. What I mean is this is a circuit popularized by Leo Esaki. That is an Esaki oscillator. And the other one, also an Esaki oscillator. What is the purpose of the circuit? These 2 circuits. Circuit, is you're taking advantage of the defect of the transistor that operates in different connection. What I mean is the negative resistance. You can see that in my previous video how to construct this Esaki oscillator, or also known as transistor avalanche breakdown oscillator. We can see that in the diagram later on. Why is it that the blinking pattern is different if they are both Esaki oscillator or transistor avalanche breakdown oscillator? Because I'm using different transistor. This one I'm using C1815 BJT. This one I'm using 2N222A. Although both have the same capacitor, but different transistor. This 2 Esaki oscillator makes the LED to blink, to flash by connecting the transistor a different way. You can see that in my previous video. These 2 are commercially available in the market. Just buy the blue blinker. There you have the LED flasher. Just connect the other LED. It will also flash in sync with the blue blinker. Or you can buy RGB multicolor fast LED flasher. Aside from the 4 circuits I also have this This is a normal LED lamp circuit. We have the push button here, one transistor, some resistors also here, but have the same circuit configuration. What is this? Transistor is functioning as a switch. Push the button, it will on. Can you convert that normal LED into this LED flasher? Yes. How? By manually pushing the button, you will get the LED flasher like this. What if your hands are getting tired of making an LED flasher using this transistor inverter circuit configuration? This is my previous project. I'm tired. So, in order to convert this normal LED circuit into an LED flasher, we're going to design a switchboard. And because of that, we have now a module, a switchboard that can control the normal LED or converting the normal LED into a LED flasher. This is now my switchboard. We have the output LED, jumper settings for manual LED switch, and also jumper settings for LED flasher. We have the jumper settings also for 5 volts and 9 volts. Power supply header, power on LED, and some resistors. So let us see how this circuit works. Let us patch the 5 volt supply, and then the negative one. Did you see how the circuit? Power LED turns on and the circuit looks like this one. See? If you push the button, LED turns off. But because this is a switchboard module, we can convert this LED into an LED flasher by just switching it, sliding the switch of the jumper, and now we have this, a flashing LED. From normal mode, using the switch. Okay, what happened to the jumper? Using the switch and an automatic LED flasher. How about 9 volts? Using a 9 volt supply, we got this. Changing the jumper settings into 9 volts. A change in the voltage will make the LED blinking pattern to change. A slower at the slower So now we have one circuit, 2 in 1. An LED flasher at the same time, a manual switchboard using 2 transistor NPN BJT. I'm using 2N3904. Also, only using one capacitor and some resistors. This is now my switchboard version of LED flasher. You got 2 function in by just changing the jumper settings. You get a manual LED flasher, and then switching it again, it becomes an automatic LED flasher in just one module. 2 functions in one. See? That is my version of oscillator circuit. Okay. If you're interested in how did I design the circuit, we are now going to an electronics engineering part. That is how we study the current flow, or we're going to see the circuit diagram. So let us see the circuit diagram of this switchboard. We get this. This is the circuit diagram. We have the power on LED, the green one, and then we have this output LED, the yellow one. I got 2 transistors NPN, 1 capacitor connected to the output feedback circuit to the input of the second transistor, 2N3904. This circuit configuration is a fixed bias circuit, and the LED is connected in series with the load resistor or collector resistor. The input of the first transistor is connected to the output of the second transistor, and the output of the first transistor is connected to the base by a C1. So I'm using 1 capacitor and 2 transistor, 2 LEDs, and 5 resistors. Why did I use this? This is now the switch side. Instead of using a manual switch connected to the ground, I'm using this transistor as a switch to the input of the first transistor. And also connected is the capacitor and the resistor. What is the circuit configuration of this transistor? Fixed bias. It seems that it is a voltage divider, but it's still a fixed bias. This part is for the controlling component, the capacitor, the charging and discharging action of the capacitor. So let us now analyze the current flow. Once you power on the circuit, current flows using 9 volts into this node, making to turn on the power LED. This is the RD2 and LED D2. So when you power on the circuit, LED turns on. So we get the first KVL in this power on LED, VCC minus RD2 to D2. Since we know that the voltage rating of the LED, we get the voltage drop of 7 volts at RD2. Using Ohm's law, I is the current rating of LED in the datasheet. We got 350 ohms. That is the value of RD2. I'm using 330 ohms available resistor. So in this circuit, we are going to solve all the values of the resistor here. This now is 330 ohms. Now, let's come to this part. VCC RC2 to QBE, not this one. In this configuration, the capacitor is charging in this state, charging through RC1, D1, C1, and passing to this node, RB2, and then the base to the ground. Also, current flows here at this node to here, and this transistor now is saturated because of the current, triggering current that flows into the base through this node, the base. And because this is saturated, it makes this LED to turn off, Q2 on, Q1 off. So the current flows into the capacitor, charging the capacitor. Still, we cannot solve the other elements, the other components. Let us see now using this equation. It seems that we need to use this figure 2 when the capacitor now is discharging. So at this state, capacitor is charging, and we know the current flows indicated by the arrow into the node. This is on, this is off. When this is discharging, current flows into the RC1, D1 to this CE, because there is a current flows into the base, making this transistor to operate in saturation. So this is on. LED turns on. Why is it that LED did not turn on here? Because there's not enough current to turn on this LED. It passes to the capacitor and to the transistor due to the charging of the capacitor. But here current flows into the RC2 and into the base emitter of the transistor, making this the forward bias. Because of that, current flows into the output side of the transistor 1, making this LED to turn on, close to the ground. So we can now use this equation. KBL at BCC, RC2 to QBE. We're going to compute for the values of RC2. BCC, voltage drop RC2, voltage drop at base emitter and to the ground. This is now forward bias. What happened here is this is cut off, because at this state current flows into here, into the base, into the other end, RB1, RB2, and to the capacitor, to the output, this feedback path of the capacitor. This is now the controlling component. That this time capacitor now is discharging, dumping its charges to the ground, making this transistor to operate in saturation. So we get now the voltage drop at BCC minus BRC2, BBEQ1 SAT. And we know that in the datasheet of this 2N3904, 0.9 volts, voltage to emitter at saturation, 8.05. We got another KBL at the D1. D1 here at the output side. BCC, BRC1, BD1, BCE set. Because transistor now is in saturation. And we know the collector emitter of the transistor 1 in saturation is 0.3 in the datasheet of the 2N3904 transistor. We got now this 6.7 volts across RC1. Okay, the voltage drop at RC2 8.5, voltage drop at RC1 6.7 volts. Okay, since we know the voltage drop here at this state when the capacitor is discharging, making this to operate in saturation. This one is off, this one is on. In this circuit, resistor is in series with the D1 LED, the output LED. Then the current is in series equal. And the current at the D1 is also equal to the current at RC1. So I can now use this Ohm's law. Since we know voltage RC1, 6.7 divided by the current of the LED that is given in the data sheet, we get now 300 ohms. I use 300 ohms, my available resistor. So we now know the value of here, 300 ohms. Now, can we now compute for the current to know the value of this RC2 by using a current gain? HAP is equal to IC over IB. And the IC collector current of Q1 is equal to the RC1 current, collector resistor current, also equal to the current of the LED. So I'm using now 0.02 and I'm using HFE of 100 for this 3904 given in the datasheet of transistor. This is by transposition because we know that the base resistor now is the RC2 here. See the current flows. This is now the base resistor to the transistor, this RC2. Transposition, calculation, we got I RC2 of 0.0002 ampere, or you can use 2 milliamps, 0.2 milliamps, or 0.0002 ampere. Since we know the current at RC2 and the voltage drop at RC2, using Ohm's law substitution, we get now 40,250 ohms resistor. But I'm using 40 kilo ohms resistor, my available. So we got now the value of RC2, 40 kilo ohms. How about this one? Why did I put a resistor here? So this resistor is some sort of commuting resistor that will serve as biasing of the transistor at the same time for the discharging path of the capacitor. What is the value of this RB1? Usually in practical electronics, we are using an arbitrary values, which is 10 kilo ohms. That is the safe value of the RB1. That is the safe value for biasing this type of transistor configuration, a base bias configuration or fixed bias configuration. Usually, we are using 10 kilo ohms. But here I computed 40 kilo ohms because this value is corresponds to the load. I designed it based on the LED, but in practical electronics you can use also 10 kilo ohms here, but I use 40 kilo ohms based on my computation. So I use 10 kilo ohms here in practical electronics that can make this transistor to forward bias. Also at the same time it is used as a coupling resistor during the discharging effect. See the arrow of the capacitor. So I use 10 kilo ohms. During the charging of the capacitor, it serves as the base resistor to the transistor. During the discharging, it serves as just a coupling resistor to the capacitor. Discharging through this path, RB1, RB2, C1, and going back to the collector of the first transistor. What is now the value of this RB2? You can also set different types of values of this RB2 so that you can now set the LED to blink whatever blinking pattern you'd like to do. So if you put a lesser value of resistor here, the LED will blink in a faster rate, faster speed, slower speed by using a resistor with big values. So I choose to use 220 kilo ohms. That is now the blinking characteristics of 220 kilo ohms. It is arbitrary because when you're going to compute for the speed of charging and discharging of capacitor using time constant tau is equal to resistor times capacitor. I'm using 220 kilo ohms, arbitrary values, and I'm using 1 microfarad. Also, the value of capacitor here is arbitrary. You can pick any values you want to adjust the blinking pattern. Converting it to farad and ohms. Again to farad, microfarad becomes 0.000301. I get 0.22 second. That is now the blinking or the time constant of the charging and discharging effect of the capacitor. And what is the frequency? You can compute by using this. Frequency is equal to 1 over the time constant. So we get 4.55 Hertz. That is 4.55 Hertz according to our computation. Now this is on, making this off because capacitor now is discharging, dumping to the ground, making this to on. This one is off. While the capacitor is charging here, this is off, this is on. So LED turns on and off due to the discharging and charging of the capacitor. That's why we have this, an LED flasher switchboard, because this transistor is serving as a switch to this transistor. This is a transistor carrying the load. This is the load side, this is the switch side, the input side. So we now know why is it blinking, because of this circuitry. Capacitor, resistor, and the transistor. If you delete or disconnect this portion and use only a manual switch here, you will have this manual LED switching board. If you connect this portion, transistor and resistor capacitor, you will have this LED flasher. So with the help of this circuit, now we have this, all the values, collect RC2 40 kilo ohms, RC1 300, die output LED, power on LED, capacitor 220 kilo ohms, 10 kilo ohms, cap transistor 2, 2N, Q1, 2N, 3904. This is now the LED flasher. This is now our circuit diagram for LED flasher with a switchboard, which is controlled by using this, changing the mode. If you're going to use the manual mode, just like this one, you can use the jumper settings. If you're going to make an LED flasher, just change the settings. It will connect to the base of the transistor. And this is the power header. We get the supply of 5 and 9 volts by changing the jumper settings. We demonstrate that, but by using 5 volts, it will blink the LED to blink much faster. 9 volts, a little bit slower. By changing the jumper settings using 5 volts, 9 volts. So we have this input header, jumper, power header. This is power jumper settings, 5 volts, 9 volts. And this is the schematic, and I use this layout. Actual layout of the circuit, the output, the transistor, 1, 2, capacitor, resistors, and this is my layout. Okay, we successfully making an LED flasher from normal LED switch. We design a switchboard. Okay, thank you for watching. Bye bye.